Hello, I'm David Gaddes. I'll be presenting our work on an automated miniaturized creatinine sensing system. Along with me on this presentation is Sun Lai, a fellow graduate student, and Dr. Tadigadapa. So firstly, I'll be discussing our concept of micro-machined quartz resonators for monitoring calorimetric biochemical reactions. Then I'll talk about how we convert the signal from the frequency domain to the impedance domain to record our measurements. I'll talk about how we've implemented this sensor to record enzymatic biosensing applications. Then I'll discuss our integration of automated fluidics and temperature control to enable real-time analysis of measurements, and I'll conclude with what we've accomplished in this talk and what we'll do in the future. So we've defined an ideal calorimetric biochemical sensor to require, firstly, a high-temperature thermometer, as well as a decoupled reactor design, which allows for the functionalization of enzymes, and also will present sensor fouling, which occurs when enzymes are functionalized on top of the thermometer. And finally, there needs to be good thermocoupling between this decoupled reaction and the temperature sensor. So we're using quartz resonators as our highly sensitive thermometer. Typically, these Y-cut quartz resonators have a temperature sensitivity of 90 ppm per degree Kelvin. We've also integrated a fluidic reaction chamber, which contains an active enzyme, and integrated on top of this quartz resonator. So we're using our quartz resonator detection system to monitor creatinine because there's a critical clinical need for monitoring of creatinine to relate to early acute renal failure. This acute kidney injury occurs in about 5 to 7% of all hospitalized patients and can result in a mortality rate of 50% of those patients. Additionally, there's an estimated $8 billion per year spent on acute kidney failure. Classically, serum creatinine was used to relate to the health of the kidney. However, serum creatinine levels typically are insensitive to early changes of kidney function. In contrast, measurements of urine creatinine are sensitive and early indicators of kidney dysfunction. However, the current techniques for continuous measurements of urine creatinine are limited and maybe will only allow for a measurement, will only allow for data points to be taken every 2 hours or so. So this is the concept of a decoupled reaction chamber and quartz resonator. So we microfabricate quartz resonators in our lab, and 100 microns for the surface, we will have a substrate which will have the reaction of the enzyme. So the reaction of the enzyme will occur on this substrate, 100 microns from the surface of the quartz resonator. This enzymatic reaction will produce a power in the order of tens of milliwatts. That power will heat up the liquid contained on this substrate, and heat will transfer to the quartz resonator, which will then detect. So here's a image of our microfabricated quartz resonator. We have 8 resonators on a single detector, so we have an array of these detectors to inevitably monitor multiple substrates at the same time using different enzymes. This quartz resonator is housed in this stainless steel packaging. The stainless steel packaging has the thickness of the top plate is 100 microns, which defines the gap between the sensor and the substrate which contains the enzymatic reaction. Here's an early design of that decoupled sensor substrate which contains the enzymatic reaction. Here we use this weigh boat made of polystyrene. The enzymatic reaction would occur here. The liquid would heat up and transfer to the quartz resonator, which we then detect with an impedance analyzer. So the temperature sensitivity of our quartz resonators are about 7 kilohertz per degree Celsius. We'll see a shift of the resonance of 7 kilohertz per degree Celsius. And additionally, has a responsivity of 7 kiloohms per watt. And as I mentioned, the power of the enzymatic reaction is on the order of milliwatts. So this quartz resonator is a great system to detect these biochemical reactions that are occurring. So finally, we come up with this process to transfer the signal from the frequency domain to the impedance domain. This allows to take a very simple recording of that biochemical process. We do this by monitoring the magnitude of the impedance of the resonator near its resonance frequency at a fixed frequency. So in this image, we would be monitoring at this particular frequency and looking at the magnitude of the impedance. when the temperature changes, the frequency would shift, and while we're looking at the same frequency, we would see a change in the magnitude of the impedance, which is what we record. This is good if there's just small frequency changes, as we use this linear region for the detection. If it goes out of the linear region, we'll no longer be able to detect the reaction. So to keep the enzyme stable, and so we don't have to keep putting more enzyme in, we immobilize the enzyme and glutaraldehyde using in this capped-on tubing. The functionalized capped-on tubing can be placed in the path of the fluidic setup that we use, and it can be easily replaced and put in with something that is a different enzyme, or if you need to replace the enzyme. That we use capped-on tubing because it's very thin and has a pretty good IR spectrum in the 8 to 12 micron wavelength range. So here's the 8 to 12 micron wavelength range. It's got about 50% transmission. That's the same wavelength that the Quartz Resonator will absorb and respond to. So the integrated fluidics that we use can be represented with this schematic. In particular here, I'm using enzyme in free solution rather than immobilized, and also there's a pump for the substrate, one pump for the enzyme in free solution. So firstly, these pumps will just take their fluid from the particular reservoir, then inject the fluid into this 3-port connector, which mixes the liquid containing the enzyme and the one containing the substrate, in which a reaction occurs and continues to flow over the sensor where it's detected. In this design, we've just minimized the volume between the 3-port connector where the two solutions are mixed to the sensor, so there's minimal heat loss, and also from the enzyme to the connector, such that less enzyme's wasted. And this can also be used if the enzyme's immobilized in this tubing, kept on tubing here. You could just use substrate and PBS to wash. So we've housed all these fluidics in our sensor in this box to reduce the noise, and so we can create a higher temperature environment for the enzyme, which would increase the catalytic rate that the enzyme could have. So inside the box, we have the box on the left, which houses the fluidics. This box has the resistive heater here to heat up the environment to 37 degrees. The box on the right houses the sensor, also has a resistive heater, so the sensor will also be at 37 degrees, which increases the rate of the catalytic activity of the enzyme in here. The fluidics look as such. We're using 2 pumps. One pump will take the solution of enzyme from the reservoir. This pump will take analyte from the solution. They'll poke both into the 3-port connector, which the hot liquid then goes to the sensor. So I had some videos, but I could not get them to work on this computer. Here, I was just going to show how the pump would take solution from one reservoir and pump in, and here a colorimetric reaction occurred. This is the capped-on tubing, which is 100 microns from the sensor. The colorimetric reaction would occur there, and this color would change from a light blue to a black. So finally, we get to some results. Firstly, we looked at the catalysis of ABTS, which is a large dye-molecule processed by horseradish peroxidase. So the reaction is hydrogen peroxide and ABTS get processed by the horseradish peroxidase to form 2 waters and an oxidized ABTS, which is colored, so you can see the colorimetric reaction change. So in this reaction, we were easily able to resolve reaction down to the micromolar range. It produced a very large output. So we just did this reaction first to ensure the reaction was occurring. Since it's colorimetric, I can observe the reaction with my eye as well. This produced a logarithmic plot based on the concentration of the enzyme and the response we got, which is expected based on the kinetics of the enzyme, the Michaelis-Menten kinetics. So then we proceeded to look at a urea-urease reaction, which hydrolyzes urea at 37 degrees. We did this test at 37 degrees rather than at 21 degrees Celsius because the rate of reaction is higher at 37, so we would get a bigger signal. From these results, we also, again, were able to resolve substrate down to the micromolar level. And again, we see a logarithmic curve, which we expected. So finally get to the creatinine that we monitor using creatinine deaminase. Since this was not characterized as well as horseradish peroxidase and urea are in the literature, we determined the enthalpy of the reaction using a commercial calorimetry device. So we heated all the solutions up to 37 degrees Celsius and then observed the change in calories per mole at different molar concentrations of enzyme to substrate. From that, we were able to determine the enthalpy of the reaction is 67.2 kilojoules per mole, which is similar to that of the urea. So finally, we used our system and with immobilized creatinine deaminase to quantify or to detect different amounts of creatinine. So we were able to detect down to the 1 molar creatinine level, which is substantially different than the phosphate buffer, which has absolutely no response. So this is in the clinical range we would want to look at if we were to monitor acute kidney failure. And again, we see a logarithmic plot from the output. All right, so in conclusion, we micromachined Y-cut quartz resonators for calorimetric biosensing. We implemented an automatic fluidic system to monitor enzymatic reactions, which was specifically designed for this and was used in the measurements. So the immobilized reaction tubing was simply placed on top of the sensor to create a decoupled reaction. And this tubing may be taken off and on easily to replace the enzyme or with a new enzyme. The configuration of the sensor allows for a robust sensing platform with no fouling because the immobilization is not directly on top of the sensor. It's removed with the tubing. And the sensor was packaged to allow for easy integration of that microfluidic channel, and real-time measurement flows were made. That's it. Any questions?